So, with all the routing algorithms that we studied in the last few classes, one was the shortest path or the Dijkstra's algorithm, that was a static kind of routing algorithm, and another one was the flooding. We have seen what is the flooding kind of routing and how the flooding is again checked, and then we studied about the dynamic routing algorithm, which is one of the routing algorithm is the distance vector routing algorithm. So, next another kind of dynamic routing algorithm or the adaptive routing algorithm is the link state routing algorithm. We have seen the problem that was occurred with the distance vector was the count to infinity problem, and we will see now how the link state eliminates the problem of count to infinity, having all the features or strength of the shortest path as well as the distance vector routing algorithm. So, to have this link state routing algorithm, basically this algorithm has got 5 prime steps. The first step of it is it learns the neighbor information, learns about its neighbors. When we talk about the neighbor, that means they are basically the one hop neighbors, or you can say the next neighbors. Next, the second step after learning about the neighbors, the second step that it follows is find the cost to reach the neighbor. We will see the details of each of these steps. Then third one is building the link state packets. Fourth one is after building these link state packets, distribution of the packets takes place. Distribution of the LS packets. And then finally applying the shortest path or the Dijkstra's algorithm locally to find the best path. Shortest path execution or the implementation locally. So, how each of these 5 steps are calculated or the executed in case of the link state routing algorithm? The first step that we say is the learns about the neighbors. Here we say about the neighbor means the next hop or the one hop neighbors. So, if you have a node A and another node connected with a point to point link, the A and B, then when the router A comes up into the network, it first tries to learn who are my neighbors in the subnet. So, to understand this, what it sends a special echo signal. A small echo packet is transmitted by the router who comes up, and with an expectation that whoever will receive this echo will send back a response. So, if multiple nodes are connected to A, all of the nodes or all the outgoing paths are sent with the same echo packet. And when the echo packet is received by the neighbor or the another node, the neighbor responds back to the sender with its own ID. That means it sends a packet containing its own source address, and this fellow also sends the same ID of its own. So, at the end of this step, A can find out who are my neighbors. The one of my neighbor is B and another is C. So, with the end of this step, every node similarly finds the who are my immediate neighbors or next of neighbors by finding their IDs, and it ensures that these IDs are unique to the subnet. Now, let us say here a question comes, let us say there is a LAN here. This LAN is connected to 3 subnets. Let us say here is one subnet, another subnet is here, and let us say another subnet is, so 3 subnets are connected. Now let us say B, and we know that B, E and I, these 3 are connected to this LAN. So when E sends an echo packet, who are the neighbors of E? In this kind of figure, on this kind of diagram, if you have a LAN like this having multiple LANs connected to connected in this way, similar way, the subnet 3 LANs, and if E is the node who sends an echo packet, from whom it should get the response? Should it get from the response from B or I or from none? Is B and I both are one of neighbors to E? Come on, say yes or no. Who says yes? Who says no? Rest says nothing. They don't exist, right? Okay. So now I'll transform the same subnet or this LAN in this way. Let's say B, E, forget the other nodes, I am just considering these 3 nodes. Can I transform the network into this? Can I? Having this as an artificial node, I am saying this is the network who connects all 3 nodes B, E and I. Now should B and E connect to each other in 1 hop distance? They should get or not? So who should get the response from E? The E should get the response from which node? B or I, or from both, or from none? Still there is no answer. None? Who says none? Who says from both? Nice. So you find out what will be the result in this. If E sends an echo, who gets the echo? It comes to the network, right? This can be considered as a gateway, virtual gateway, or a node who should respond back, not B and I, right? So this there will be different scenarios and topologies in which the node which is 1 hop neighbor are directly connected to a node who is sending the echo packet sends back the ID, and now A has all the information about its own neighbors, and that is all at the end of the first step. Coming to the next step, that is calculating the cost to reach each of the neighbors. If B is one neighbor, if C is another neighbor, how it can find the cost? If the cost is of number of hops, then the cost will be definitely 1, as we discussed earlier, right? And basically it is a confusing one. We usually do not consider the number of hops as a cost to reach, because you never know what will be the actual geographical location between the nodes. So they are usually not considered as the cost to reach in the next hop. So how the cost could be calculated from one node to the another node? Let us say the same configuration A, here is B and here is C. Now to execute the second step of the link state algorithm, what A does, it sends a special packet. I am sorry, the first one is a hello packet. Replace this with a hello packet, because they just try to introduce with each other. This is a hello packet, and this one is the echo packet. Replace this echo with the hello packet, and the second one, when it tries to calculate the cost to the neighbor, it sends a special packet called the echo packet. And this echo packet is transmitted in the same direction from which it gets a response in the previous step. So 2 echo packets will be sent in this direction and along with this direction. and the receiver who gets the echo packet immediately sends back the reply to it. So, you have a calculation of the RTT in every direction, and dividing the RTT by 2 will give you the cost of arriving or cost of reaching the destination or the individual neighbors. So, your hello packet identifies your neighbors, whereas the echo packet finds the cost to reach the neighbor. Now, again there is another case here. Let us say the node A who is sending the echo packet has several other packets associated with it. That means there is already load associated with the subnet, right. So, when this will generate the echo packet, what will happen? When already there is a traffic in the path for the destination B and C, and this node A generates an echo packet, what will happen to the echo packet? Can anybody answer to this? It will be encoded, right? Meaning what? You have several other packets which are already in queue and they are buffered, they are to be transmitted prior to the echo packet. So, you have the network designer has two options. Either it calculates the RTT, when it takes the RTT, it considers the queuing time with queuing time or without queuing time. Without queuing time means when the echo packet comes to the front, that means when it is actually released into the network. So, two options are available. If the load has to be considered, so you are considering the queuing time. If no load has to be considered, then in that case it is considered when the echo packet comes to the front of the queue and actually it is released to the network. Why this is so? When this kind of scenario comes into picture, let us say you have a subnet like this, you have the subnet having this topology and we say they are actually in the opposite directions, the nodes are in totally opposite directions. So, ABCD you have in the west and EFGH you have in the east. Now, you have some packets to be travelled from the west to east. So, they have two options, either this path I will say this is path 1 or this path I will say this is path 2, right. So, there will be a scenario when all the nodes of this network or this subnet will follow the path 1 all the time. So, when they follow the path P1, because earlier it was calculated that P1 is the efficient path or the RTT was less in this case, P1 RTT was lesser than the RTT of the P2 earlier case. So, what they did choose, they choose the path P1 as an efficient path or a optimal path from the east subnet to the from the west subnet to the east subnet. So, all of the paths, their packets, they try to follow this packet or follow this path. So, at one point what will happen? This path will be overloaded because the packets that are being generated here will try to be enter into the queue which has already been built in. Because the packets from this direction, everyone is trying to follow this path. So, when the load is considered, you will find that at one point the RTT of the previous case, which was found to be an optimum one or the best one, is degrading. So, in that case what will happen? If load is considered, you get the actual path here. After some point of time, we will see this, what is this called is congestion, we will see this what is congestion. So, after some time you will find that this path P2 will have a better RTT than the P1 RTT when you consider the load. So, after some point of time, the packets having executed with their routing algorithm will find P2 to be a better path than P1, and they will try to follow this path. So, this is what is the dynamism. The path will change as per the scenario of your network. If you consider the load in this case. If you do not consider the load, always you consider when the queue or the packet, the echo packet comes to the front, definitely you will get always this same RTT in both the cases, because you are not considering any of the factors in the path. So, it decides or it depends on the network designer to find out the changing path, or he has to follow the same path, or depending on the number of packets that can be accepted or the overload can be accepted, it is decided whether you consider the load into the path or you do not consider. But that is how the cost to reach to the neighbors are calculated. So, by the end of the second step of the link state algorithm, you have the list of nodes for every node in the subnet and the cost associated with each node to the neighbors. The third step of this algorithm comes to the building of the link state packets. Now, every node now tries to build up a link state packet with its own address. Let us say A is building the packet, so having two neighbors A, B and C. So, if A is building the link state packet, it puts its own ID at the top. Then two more fields, we have already studied about this field, sequence and the aging field, followed by the neighbors that it has studied B and C, and the cost to reach to those neighbors, if it is 5 and 3, then 5 and 3. This is the link state packet of A. Why these two fields sequence and A's are attached to this link state packets? Can anybody answer to this? We have already studied about that. If you remember the sequence field, the flooding kind of routing algorithm, right? So, to damp the number of floodings, every packet is associated with its source ID and the sequence number of the packet generated. Who stamps this sequence number is the source. So, if A generates a packet, it says that this is P1 of the source A. This is stamped all the time, so that when it is flooded to the neighbors, it is never re-forwarded, because every packet is stored and forwarded in the flooding case. So, to check the flooding, number of forwardings or number of floodings, if the same packet has already been forwarded by the same host earlier, that is what we studied in the flooding algorithm, right. Every node who forwards a packet maintains a list, and whenever it forwards a packet, it checks the list whether I have already forwarded the same packet generated by the same source or not, because P1 can be again generated by C, P1 can be generated by B again. So, the same source along with the same ID or the sequence number, if it has already been forwarded by an intermediate hop, it never re-forwards it. So, to check the number of floodings, we have this field sequence number. Aging is also another way. Let us say I say that my packet can, or the A says my packet can travel maximum 100 nodes. So, every time it visits a node, the age is decremented by 1. So, now it comes to 99. Next time when it is forwarded, again it goes to 98, this way. And when it comes to 0, when the age comes to 0, the packet is automatically dropped. That is also another way of damping the number of floodings in the subnet. But provided if you know what is the total dimension of your subnet. If your subnet is having 1000 nodes and you put the age as 100, then it will hardly travel 1/4 of your total subnet. So, if any node has its own prior knowledge of the subnet that I belong to a network when the number of nodes attached to this is 1000, then it has to give the A's at least 1500. So, multiple visit of the packet by the different nodes is acceptable, but not the minimum one. So, that is how your A's and the sequence number fields are important in case of your linked state packets. And the rest of the things that we studied in the previous two steps, the source, the neighbors and the cost to reach to the neighbor. So, at the end of the third step of linked state algorithm, all the routers will have this kind of linked state packets. Now, can you answer me one question? We have studied another table, routing table, right? Every node in a subnet maintains a routing algorithm, a routing table. Who says who is my next hop or the best hop? The preferred path, what we studied. Is the routing table same as your linked state table? Or the routing packet, you mean to say, if I say this is the routing packet and this is the LS packet, can they be same? Linked state packet contains the information about the neighbors. Routing packet is the packet that contains the data, right? And if the linked state packet comes to a node, let us say it comes to a node, routing A, it has its own routing table of A. And when it receives the linked state table, it gets all the packets from this to update its information. So, this is not at all same as your linked state table or the linked state packet. So, linked state packet gives only the local information of any node, which gives the current status of the node along with its neighborhood. That is what is your linked state packet. So, this is at the end of your third step of the linked state algorithm. Now, coming to the next one, next step is distribution of the linked state packet. The fourth step of the linked state algorithm is the distribution. So, if A understands or A builds up its own linked state packet, after building this linked state packet, LS packet, it has to distribute to everyone, so that they will update their own routing tables accordingly. And one of the efficient method of distributing this is flooding, because usually the flooding is preferred for distribution of the LS packets. So, you have those significant fields, that is the A's and the sequence number fields, so that those packets are flooded and are again checked after some time or damped after some time, right. So, this is the flooding is one of the method for distributing the linked state packets. And finally, once this is flooded, your linked state packet of A, LSA arrives at B and LS of A arrives at C. Now, they update their routing table to find the best path to the other nodes of the subnet. So, that is what is your final step, the finding the local minima, or what you say the shortest path algorithm is executed. Or the Dijkstra's algorithm is executed here to find out the shortest path to every other node in the subnet. And we know what is this shortest path algorithm is, right. So, with all these 5 steps, now can you realize how the count to infinity problem of distance vector algorithm is eliminated? Remember the case of your count to infinity problem of your distance vector algorithm, A, let us say A, B, C, D and E, 5 nodes were there, right, and there was a link to X which was disconnected. And what happened in that case? All the nodes, they tried to increase their routing tables, cost of the routing tables, and they found ultimately they could not reach to X, but somehow they increase their number of hops, and that was the count to infinity problem. Now tell me how link state can stop this. So when the LS is executed at A builds its link state table saying, let us forget that sequence and A's and all those things. Now the neighbor is B, some value, let us say 1, let us say 1 hop, and if X was earlier the neighbor, now it comes to infinity. So when this is done and this link state packet is sent to B, and B when updates its routing table, now it understands that A cannot reach to X anymore. So I cannot increase my number of hop count to 3. Earlier if it was 2, it cannot 3, because now it understands that I have to reach to A, and A has an infinity value. Earlier what A was doing? A was doing through B, it was increasing to 2. So when A finds its neighborhood, it knows that X was earlier my node, so there was a cost associated with it, and now no more X is responding me back, so A is no more my neighbor. X is no more my neighbor. If X is no more my neighbor, I cannot reach to X, and this is the table he sends to B. And B receiving this link state packet of A understands that I cannot reach to A because my neighbor is A, who was earlier reaching to X with a step of 1, and this is how your link state table or count to infinity problem is eliminated with the link state routing algorithm. It follows the same path of your static routing algorithm, the shortest path. It follows the vector updation, that is as your distance vector algorithm, exchanging the tables, updating the tables globally, everything. But only thing, the new thing that is adapted in the link state packet to avoid the count to infinity problem is detecting the neighborhood and finding the cost to the neighborhood. That is what is the link state routing algorithm, and most of the routing algorithms even today for the wired network, wireless network, your PAN, BAN, anywhere, you will see one part of the component is either the Bellman-Ford algorithm or Dijkstra's algorithm or the link state algorithm. And what the count to infinity problem is also called the looping problem. So you will see any routing algorithm, when you validate it, it first says that there is no looping. No looping means you do not have the count to infinity problem now. There is always a termination. If there is no path, you do not have any path to that. It says there is no path. So no more searching to that node if there is no connectivity. This is what is your different kinds of routing algorithms, like your shortest path, the flooding kind, there are the distance vector and the link state routing algorithms. Now with all these routing algorithms, if you find there is one term associated with the routing algorithms, if there is a path, if there is a link between two nodes, this link has definitely got a capacity called the maximum carrying capacity. Or usually we say MTU, the maximum transportation capacity or transfer capacity unit, MTU. Usually we say the maximum carrying capacity of a node. Now let us say we have a path between A and B, and A is transmitting and the packet has to be delivered to A. The link has a capacity of 1000 packets. So this is the MTU. And the packets generated by A are, you have the 100, then 200, 300 up to 1000. Again there are 1500, let us say 2000 this way. So 100 packets are generated by A. Can they be carried with the, or the link can carry them easily or not? Because it has a capacity of 1000. So 100 packets when it carries, it delivers all the packet to the receiver. So all the packets are delivered. If this is the number of packets, and this is the number of packets delivered. If you draw a graph in between, then the number of packets when it goes up to 1000, you will see that the delivery rate is almost same. Let us say this is 1000, let us say this is 200. The ideal case is that till 1000 packets are generated by A, all the packets will be delivered. The reason behind is it is less than equal to the maximum MTU of the link. Now you still go on adding the packets into the subnet. Let us say it goes to 1200. What will happen? The ideal case is that slowly it should go on delivering the packets at a constant rate, but that is never possible. What happens when it comes to actually the desirable case is even after some time, even it degrades. The reason behind is, we will see what are the different possible reasons. It degrades and again it continues in a similar way. If this is the ideal case, we say this is a desirable case or an average case you can say. But the practical case or the worst case scenario is, if you go on increasing the number of packets, after some time what will happen, your packet delivery, number of packet delivery goes on reducing, and at one point it is almost null. So at this scenario we say there occurs a problem in the network which is termed as congestion. Congestion means a situation when the number of packets in a route between any sender and any router, any receiver, goes beyond its capacity. So it is a global issue, or you can say this occurs in any subnet. It can occur in any link of the subnet. If you have a subnet like this, congestion can occur anywhere. If this is the sender, the receiver, it can occur here, it can occur here, anywhere it can, in any path the congestion can occur. It is not like that when it is started and it goes to the next stop it occurs, no. So if anywhere in any link of between the sender and the receiver there is a number of packets more than the MTU, we say that the congestion is occurred in the subnet. So what are the factors that causes the congestion? Let us say you have a topology like this. This is a node A, B, E, F. B is a node which receives the packets from A, forwards it to C. B is also a node who receives the packet from F and forwards to C. So when earlier it was receiving the packet from A, we say that this is the best case. It is only receiving the packets from A and it is forwarding to C as per its link capacity. Now B also receives the packets from F. So the number of packets with respect to time is now more as was expected from the previous case. So when the packets comes here at B, what will happen? Now B has the packet from A as well as F. Routing meaning what? When we say it forwards the packet or routes the packet, meaning what? It receives the packet, what we say is a storing, then it forwards the packet. So routing means the other name is store and forward. It receives the packet, buffers it for a while, then forwards it. So during the buffer, what we say, it makes a queue of the packets, it builds up a queue. So when the packets comes from A and F to B, they are entered into a queue at B, and then B forwards the packet to the next hub. So what happens at B now? If the B node has a smaller buffer, what will happen? Let us say B has a small buffer. What will happen? A will send the packets, F will send the packets. If this fellow is not able to buffer them, the packets will be dropped. If the packets are dropped, what will happen? Again these two fellow will retransmit because of the timeout, you know. So, every time they transfer the packets, they will be dropped. So, more and more packets will be transmitted in this line then. So, congestion will occur at this point, congestion will occur at this point. The reason behind is, earlier A was sending the actual packets, but now A is again sending the retransmitted packets. So, along with the data packets, those are supposed to be sent, again it is retransmitting the packets for which it got the timeout. So, the congestion will occur at this link, and congestion will occur at this link, because the forwarding node has got a lowest buffer, I mean smaller buffer size. The solution is, you increase the buffer size. But again Nagle says, one of the researcher, he says, if you increase the buffer size, still then occurs a problem. Let us say you increase the buffer size to a high value, very high value. You have to find the optimum of that. What will happen? Whatever packet will come to be, they will be buffered here. Earlier you have a small buffer, now you have the sufficient buffer size, but your processor at B is slow. Slow in the sense to handle so many packets in the buffer. Earlier it was able to handle this many number of packets as per its buffer size. Now you increase the buffer size, the processor remains same. So, now the processor of B is not able to handle so many packets in the buffer because it is not compatible. What will happen again? They are still in the buffer. So, moving from the buffer to the actual channel takes time. What will happen? Same problem, timeout, and again this fellow goes on increasing. They are adding their packets into the buffer, and same packet is being transmitted. When it transmits, same packets is being transmitted. So, you have a congestion, you have a loss of bandwidth or consumption of bandwidth for transmitting the same packets multiple times. So, either if you have a smaller buffer, you have a slower processor, or you have a the bandwidth is less. This is the same case. If this bandwidth or channel capacity or link capacity is less, again you will see the same condition of your congestion that has occurred. So, usually these are the three factors that causes the congestion in any network. So, any algorithm that has to be found out has to be optimized, or a trade-off has to be found out with respect to the buffer size, the processor speed, and the bandwidth of the network associated with it. If you remember, we studied about something flow control, right? And this is something called congestion control. That was flow, this is congestion. How these two are different? What is flow control? What is congestion control? Can anybody answer to this? We have something congestion that we saw now. We had something flow that we already studied in the data link layer, flow control. You have the flow control protocols, the sliding window protocols, the stop and wait protocols that handles the flow control, that controls the flow between the sender and the receiver. And here it is a congestion control. Sounds similar? Number of packets are more and they are not able to be transmitted, they are being dropped, your timeout occurs, all those things. So, how these two are different? If you see, congestion is a global issue which occurs in a subnet, whereas this is global. Whereas if you consider the flow control, where it occurs? This occurs only in a point-to-point communication, right? We have seen this. So, this is a local issue. So, when we talk about flow control, we talk about two nodes connected in a point to point fashion, and this is a sender, this is a receiver, and how the sender sends the packet that matches with the speed of the receiver. So, they build up a sliding window, they build up a window that slides or that shrinks or expands or whatever happens with them, so that the packets between these two are in sync. The number of packets transmitted are received by the receiver with the help of a window. So, this is a point to point issue. Two nodes directly connected and the window between them handles how many packets can be transmitted and can be received. So, that is absolutely local to the sender and the receiver connected in a point to point fashion. But when you talk about the congestion, you do not see where is actually the sender and the receiver. It happens all over the subnet. Wherever can be the subnet, the congestion can occur at any point of time, but the worst sufferer are the sender and the receiver. They may be physically apart from each other, and when they are in the same subnet or they are in a different subnet, it can happen anywhere in the net. So, that is what is a global issue, what we say is a congestion. This is what the sender and the receiver are in the same subnet. Let us say this subnet is connected through a gateway to another subnet where your receiver is there. So, your congestion can even occur at the gateway. Even if the congestion occurs at this point, it will affect the sender and the receiver, which are differently located in two different subnets. So, congestion is a global problem, is a global issue, whereas your flow control is a local issue. So, how this congestion can be handled? You know, flow control directly DLL, the data link layer of the sender and the receiver, they talk to each other, they find out a solution so that the data is transmitted and there is no loss of data. But in this case, how the congestion will be handled and how the congestion can be controlled and what are the congestion control algorithms? We will see them in the next class.